All right, we're going to start with power functions, page 45. Okay, we have graphed some parent functions. We are moving into polynomials, and we're going to start with just the power functions. Okay, so a power function is any function in the form f of x is equal to a times x to the n power, where a cannot equal 0 and n cannot equal 0. Okay? So if it is a power function, a can't equal 0 and n can't equal 0. Because if a equals 0, then what does f of x equal? 0. And if n equals 0, what would f of x equal? Is it 1 or is it a? It's a, because this would equal 1, which means it would equal a, right? Okay. So then it's not a power function, basically. Now, it goes on to say a power function is also a type of monomial function. Monomial meaning one term, polynomial meaning many terms, right? So we're going to draw a sketch of each. So notice that we're talking about power functions here. This is just the monomial functions. So not all of these are necessarily power functions, but a power function is a type of what we're about to graph here. So a constant function is not a power function because it doesn't have a power or a variable, but we would just say f of x equals c. And would that be a horizontal or vertical line? Horizontal, because if it was vertical, would it be a function? No. Okay, so it would just look something like this. Okay. Linear would be f of x equals what? X. Something like that. Quadratic, f of x equals what? X squared. So it's like a parabola. Or it's not like a parabola, it is a parabola. Cubic, f of x equals what? X cubed. Looks like this. And then quartic, what do you think that's going to be? F of x equals x to the fourth. What does it look like? Anybody know? Looks like a parabola. Looks like a parabola, it's just skinnier. Because think about this. For a parabola, we have 0, 0, 1, 1, negative 1, 1, 2, 4, right? For a quartic, I would have 0, 0, then 1, 1 still, right? And negative 1, 1. And even if this was x to the 20th power, and when x is 1, what would y be? 1, right? We see just 1, 1, because 1 to the 20th power is still just 1. Okay, so then the fourth, it's just going to be here and here. What's 2 to the fourth power? 16. So at 2, I'd be at 16 instead of at 4, so it just gets taller and skinnier quicker. Okay. Quintic, what do you think that is? F of x equals x to the fifth, right? And then what do you think it's going to look like? Skinnier, the skinnier version of what? The cubic, exactly. That is it, because if I'm at 0, 0, it's 0, 0, right? Or if I'm at 0, I'm still at 0. So 1, if I'm at 1, 1 to the fifth power is 1. Negative 1 to the fifth power is negative 1, right? And then it's just going to get skinnier quicker, but it has the same shape. That's not, we're talking monomials. Monomials, right? Polynomials can have different things going on in the middle of them, but monomial functions looks like this. Okay, we good? So any monomial to an odd power is going to look like what you think of as a cubic, and to an even power is going to look like what you think of as a parabola. Okay, we good? So, symmetry. If the function has an even power, okay, so you can look at those graphs there, then it is symmetric about what? What? The y-axis. Good. Okay. So if it has an even power, with a monomial, we're talking, that's what we're talking about here, so it's just even functions. Then if the function has an odd power, then it is symmetric about what? The origin. Good. Because we have that rotational symmetry then. Everybody okay with all that? Awesome. So now let's talk about end behavior again. Okay, so some of us struggled a little bit with end behavior at the beginning, but I think we've pretty much got it now. So the end behavior of an even power with a positive coefficient. Now this is x squared, but it's talking about any even power, right? As x approaches infinity, f of x approaches what? Infinity. Right? Mm-hmm. Then as x approaches negative infinity, f of x approaches what? Infinity. Okay. We good? So I want you to do even power, negative coefficient, odd power, positive coefficient, and odd power, negative coefficient. Look at those, see if you can get those filled in without me. Okay, so for the even power negative coefficient, as x approaches infinity, f of x approaches negative infinity, and the same thing for when x approaches negative infinity. We agree with that? Okay, and then for the odd power positive coefficient, as x approaches infinity, f of x approaches infinity, yes? And as it approaches negative infinity, f of x approaches negative infinity, right? And then over here, negative infinity and infinity. We agree with all that? We good? Awesome, good deal. All right, let's flip this over. All right, so we're going to graph these. So it says graph each function and identify its key characteristics. So this is x to the 6th power. But the parent function for that just looks like what? Parabola, right? So there's my little parent function, yes? What does that 3 do? Vertical stretch of 3, right? So if I start with my anchor point at 0, 0, well, it's still just 0, 0, right? And remember, for anything with any monomial or power function with an even exponent, my other two anchor points could be 1, 1 and negative 1, 1, right? So if I go to 1, 1, then I have a vertical stretch of 3, which just changes my y value to 3, and then I have symmetry over here. So if I substituted it in 2 to the 6th power is a pretty big number, and then I have to multiply it by 3. Is there any chance of it being on my graph? No. So it's like way, way off my graph, which means this is going to be pretty skinny here, and it just looks like this. Because we know that we're going to have symmetry up there, and it's going to be like way off my graph up there. All right, so my domain here. What's the domain? Okay, all real numbers, so negative infinity to infinity. Range would be from what? 0 to infinity. Do I include the 0? Yes. So when people were getting back their homework last period, somebody said, oh, you took off 5 points because I didn't put a bracket. No, I took off 5 points because it was wrong, right? Okay, it's not just, ooh, I didn't put the right thing. Well, yeah, that makes your answer wrong. You're saying something different, so it matters if that's a bracket or not. All right, x-intercept is what? 0, 0, and if your x-intercept 0, 0, what's your y-intercept? 0, 0. Is this increasing anywhere? Yes, from 0 to infinity, and it's decreasing from negative infinity to 0. Good. And we have symmetry about the what? The y-axis. Good. Do I have any discontinuities? No, so it's none. My end behavior, as x approaches infinity, f of x approaches what? Infinity. As x approaches negative infinity, f of x approaches what? Infinity. We good with all that? Any questions at all? All right, awesome. So let's look at the next one. So we have negative 2x to the 5th power. So this is an odd power function, which means my parent function looks very similar to a cubic, right? That negative is going to do what? Reflected in the x-axis, and then that 2 is a vertical stretch of 2. All right, so 0, 0, that negative and the 2 do nothing. I'm still at 0, 0. My next anchor point would be 1, 1, and then I'm going to reflect that in the x-axis. vertically stretch it by 2. And then negative 1, 1, I reflect it and vertically stretch it. So I have those 3 points there. Then when I go to 2, 2 to the 5th power, is that a pretty big number? And then you got to double it. Is it going to be on my graph? No. So we just know it's going to be skinny, and it looks something like this. With arrows. My domain, negative infinity to infinity, right? What's the range here? Negative infinity to infinity. What's my x-intercept? 0, 0, which means my y-intercept is 0, 0. Is it increasing anywhere? No. So I have none for that, and it means it's decreasing from negative infinity to infinity. We have symmetry about what? The origin. Any discontinuities? No, so we're saying none. End behavior, you can get this in as x approaches infinity, as x approaches negative infinity. Okay, so as x approaches infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x approaches infinity. Okay. Everybody good so far? Okay, I know you pretty much got the hang of it, but we're going to do the third one anyway. I know, I figured you'd be excited. All right, so this is a 4th degree power function, which means it looks very similar to the parent function of a quadratic. That negative is going to reflect it in the x-axis, and that 1/2 is a vertical compression. Okay, so 0, 0 is still 0, 0 because the negative and the 1/2 do nothing to it. But that 1, 1, I would reflect in the x-axis, vertically compressed by 1/2. You get those. When I substitute in a 2, 2 to the 4th power is what? 16. And then that 1/2 times 16 is what? 8. Is that going to fit on my graph? Yeah, then it needs to be on my graph. So at 2, I'm at negative 8. And at negative 2, I'm at negative 8. And then I can get my graph drawn in. Okay, so if they fit, they need to be on there. Domain, negative infinity to infinity. What's the range? Negative infinity to 0. Do I include the 0? Yes. X-intercept is 0, 0, so the y-intercept is 0, 0. You go ahead and fill in the rest. You should be able to fill that in without me. Alrighty. Do you agree with me? Yes. Do you have any questions at all? Awesome. All right, so then go ahead and grab the green one. Let's talk about polynomial functions. This is going to go on page 46 when we're done. All right, so a polynomial function is a function in this form, which looks horrendous, right? But it's just because that's pretty much the definition of it, and we have to say it this way when we don't know how many terms we actually have. But I have a sub n times x to the n power, so then this becomes x to the n minus 1, n minus 2, all the way down to 2, 1, 0 for my exponents. And then the a sub n, because those are all my little coefficients, right? So it says the coefficients are real numbers, and a sub n cannot equal 0. Because if a sub n equals 0, then that first term there doesn't even exist, and that changes the name of my polynomial. And n is a positive integer, okay? So n also has to be a positive integer. So no negative numbers, no rational exponents or anything like that. No negative exponents. Okay, so shape and continuity. So this is kind of a description of the shape, so it's very unofficial wording, but just so you get an idea of what they look like, although you should know what they look like. But so polynomials, polynomials are smooth curves. Well, hang on, you can't even tell them all. Curves. Smooth curves with no breaks and continuous for all real numbers. Then the degree. Okay, so the degree, the highest exponent, which would be n, is called the degree and polynomials are classified by degree. I tried to make that as least wordy as I possibly could. So the highest exponent n is called the degree, and polynomials are classified by degree. So we could have a 5th degree polynomial, something like that. So some examples. It says, identify the degree and classify each polynomial function. All right, so if I look at this first one, what's the degree of this polynomial? Okay, so if I have, there's not an x on there. So if I force an x on there, what does the exponent have to be for it to be equal to that? Because that equals 2 times 1, which is 2. So what's your degree? 0. And what do we call that kind of function? Constant. Okay. Is a constant function. All right, so what's the degree of this one? 1. What's the degree of this one? 2. So here's a big mistake you could make as you're going along. Don't just take the first one, right? It's not the first exponent. It's the highest exponent, which most of the time will be the first if it's actually written in order, right? And that's the way we should write it. But they could, if they're out of order, it's still the highest one. And so these do go 3, 4, 5. So what this is a linear. If the degree is 2, what's it called? Quadratic. What's the third? Cubic. Yes, good. Quartic. And then what's the 5? Quintic. What about 6? It would either be hexic or it could be sextic also, because those are either one of those work. 7, septic or heptic, either one, septic or and then octic for 8, right? So it's the same prefixes that you're used to. It's really not that bad to get them in there. Okay. All right. Now, in behavior again. In behavior, we've repeated this like a bazillion times over the last few weeks, right? So do you think it's important? Nah, it's not important. We do it like every single day, but that's because it doesn't really matter. Yeah, it's important, okay? And I know this is repetitive from what we just did, but I'm going to add something to this as well. So here's what's important. Once we get to polynomials and trying to figure out how to graph them and whatnot, the power and the coefficient of the leading term determines the end behavior, okay? So we're looking at end behavior. So if we have an even power and a positive coefficient, oh, throw my pen at myself. All right, then I know that as x approaches infinity, f of x approaches infinity, right? So as x approaches negative infinity, f of x approaches infinity. So again, very repetitive. You've got this down now, right? So I want you to go ahead and fill in the rest of these, but then don't flip the paper over because we're not done. Let's just fill that in, then I'll talk about the other part of it. So just do this on your own. You don't need me. So all the times you've had to write it and your hand hasn't fallen off yet. See? Told you, you would be fine. All right, so here's the thing, is that the pictures here, I think, are a little bit misleading. And even the little equations, because it's not just if it's a quadratic, if it's an even power with a positive coefficient. We are concerned with end behavior. As we move from the power functions, from the monomials to the actual polynomials, then if I have an even power and a positive coefficient, they're not all going to look like parabolas. It could look like maybe this. It could look like this. Something like that. Okay? So my polynomials with even that are even powers could look something like that. So the middle, remember, this is end behavior. I don't care about the middle behavior. So they're not always going to look exactly like this. The picture you really need to have in your mind is not this. It needs to be this. And if you know that it is an even power with a positive coefficient, that's literally the end behavior. We don't care about the middle right now. Okay, it's up. And if you can get this little pink picture in your mind, then you can write this out just fine, and you know what the end of your polynomial is going to look like. And then if it's an even power with a negative coefficient, your end behavior looks like that. I don't want you to be confused about what's in the middle there, because then even the odd ones could look something like this. I mean, there's lots of things that could be happening, but so if I have this, my leading coefficient, is it positive or negative? It's negative, and the power is even or odd? Odd, because doesn't it resemble that last one? But not the middle part of it, because we don't care about middle behavior. This is end behavior. So odd power positive coefficient, it's going to look like this. It's going to look like the end of the cubic that you're used to. An odd power negative coefficient looks like this. Does that make sense? We're just talking about the end. That's important. If you know how it ends and how it starts, right? It's like this, like a little robot. It's up, up, down, down. It's one of those. You only have 4 choices. You only have 4 choices. You only have 4 choices. Okay? We good? So end behavior, that little pink picture there, that's important for you. Any questions? All right. So we're not going to do all of these because, again, I don't want your hand to fall off or anything, but we're going to do a couple of them. Let's do number 1 together. So it says, using the leading term, we give the end behavior of each polynomial function. So I think the easiest thing to do is to come up with your little pink picture first. Obviously, it's always going to be pink, but you know what I mean. It's even, right? So are the ends going to be the same or different? The same. And it's negative, so are they up or down? Down. So once I've got this, then I can write out my words pretty easily. As x approaches infinity, f of x approaches what? Negative infinity, right? Because it's pointing down. Then as x approaches negative infinity, f of x approaches negative infinity. And what would this be called? Since it's a 4th power quartic. 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 All right. So I want you to do 2, 3, and 4. Okay? Let me give you a minute to do 2, 3, and 4 on your own. So for number 2, what would you call this? quintic, right? Quintic. All right. So is it up, up, down, down, up? What is this? Up, down, right? Looks like this. Okay? Which means that as x approaches infinity, f of x approaches negative infinity. And as it approaches negative infinity, approaches infinity. Everybody okay with all that? All right. So what would we call 3? Quadratic. Good Lord, we should not have trouble with that one anymore. Quadratic. All right. Up, up, down, up. What is it? Up, up. All right. So that means whether x is approaching infinity or negative infinity, the y values are approaching infinity. What would we call number 4? Heptic. Heptic. Or septic. Septic works also, but heptic. Okay. So up, up, down, up. What is it? Down, up. Okay. That's what your cubic would look like, right? We're talking end behavior here. So as x approaches infinity, f of x approaches infinity. And as negative infinity, it's negative infinity. Okay. Everybody okay with that? That end behavior, whichever one, up, up, down, that's going to be important for us to get our polynomials sketched correctly. We good? Because we're going to be sketching them, not straight up graphing them, and there is a difference with that, and we'll talk about that when we get there. All right, so let's look at 7 and 8. 7 and 8 said, describe both the power and coefficient of the leading term of the polynomial given the shape of the graph. Now, I don't expect you to be able to give me the equation. I don't expect you to actually give me the power even necessarily at this point. What I do expect for you to know if it's positive or negative and if it's even or odd. Not an even or odd function, but an even or odd power. Okay? So would this be an even or odd power function? Odd, because it's different, right? It's off. So this is going to be an odd power. Would that leading coefficient be positive or negative? Negative. Good. Odd power, negative coefficient. Okay. So the number 8, even or odd power? Even. Is it an even function? What do you think? By looking at it, is it an even function? No, because we don't have symmetry. But it is an even power, okay? Even power, and is the coefficient positive or negative? Positive. Good. Okay. Everybody okay with that? Any questions at all? Awesome. All right, so let's talk about turning points. Okay? So your turning points, and we've talked about these a little bit already, the points at which a polynomial function switches direction, right? So I'm here, I'm decreasing, I switch, I'm increasing, I switch, I'm decreasing, I switch, I'm increasing, I switch, I'm decreasing, right? So if the turning point is higher than the nearby point, it's like this point right here, it's higher than the points that are around it. So what would we call that? Relative maximum. Good. So this would be a relative maximum. Then if the turning point is lower than any other nearby point, not than any other point, but any other nearby point, what do we call that? Relative minimum. And we have talked about minimums and maximums already. So maximum and minimum values, what's the term that encompasses both of them? That's what? I heard it. They are critical points. We can be a little bit more, you're right. It falls under that category. Extreme, I think I heard it. Good. Extreme. It is, the critical points are true too. All right, so then it says turning points defined where the function is increasing or decreasing. It's where it switches, all right? Now there's going to be a lot of things we can find out about our polynomials algebraically. Actually figuring out the values of the maximum and the minimum. The reason this says the calculator is because right now you can't do it without the calculator. And all the calculator is going to do is go, boom, find it for you, or you can trace and guess at it, but you're not actually doing any math there. If you know what they are, that's good enough right now. Because to actually find them algebraically, you're going to need to know some calculus. And you're not in calculus. You're in pre-calculus. That's why we're doing the beginning part of it. Does that make sense to you? So we're just going to leave this. I left it on here, though, because that's how we would find them. But again, what's the point? Just so that we can go graph it accurately, all we're doing is finding it with, we don't even know how to find it anyway. So that's why we're going to be sketching them and not graphing them. We're not going to have all the exact points, but that's okay. We don't need them. That's not what we're supposed to be doing anyway. Okay? We good? Any questions at this point? Awesome. Then go ahead and get both of these glued in. Remember, you're only doing the front of the assignment. One of them only has a front. The other one, there's 3 graphs on the front and 3 graphs on the back. You don't need to do 6. That's why I'm just having you do the front.